Welcome. Today we're diving into one of the most mind-bending concepts in mathematics, the Banach-Tarski Paradox. It reveals how infinite mathematics can sometimes clash with our understanding of reality. Get ready to explore the idea of decomposing a sphere into two identical copies of itself. So, what exactly is the Banach-Tarski Paradox? It states that a solid ball can be divided into a finite number of pieces, and, through rotations and translations, reassembled into two identical copies of the original ball. In simpler words, you can take one sphere, cut it into pieces, and put those pieces back together to make two spheres of the same size. Let's take a moment to look at the history of this paradox. In 1924, Stefan Banach and Alfred Tarski proved this surprising theorem. The proof relies on a mathematical concept called the Axiom of Choice, which we'll explore further. Stefan Banach was a Polish mathematician, and Alfred Tarski was a Polish-American logician and mathematician. To understand the Banach-Tarski paradox, we need to grasp a couple of key mathematical concepts. First, the axiom of choice, which allows us to select elements from infinite sets, leading to the possibility of non-measurable sets. Second, group theory, particularly the use of free groups and rotational transformations in 3D space. These concepts are fundamental to the paradox. Let's delve deeper into the axiom of choice. It states that for any collection of non-empty sets, there exists a function that selects exactly one element from each set. This seemingly simple axiom has a profound consequence. It enables the construction of non-measurable sets. A non-measurable set is a set for which it's impossible to assign a size. Another important concept is free groups. The Banach-Tarski paradox uses rotations around two axes that generate a free group of rank 2. This free group, denoted as F2, allows for infinite combinations of rotations. It's like having a set of moves that you can combine in endless ways to rearrange the pieces of the sphere. So, how does the decomposition process actually work? First, we partition the sphere, dividing it into finitely many pieces using the group actions we discussed earlier. Then we transform these pieces by applying rotations to rearrange them into two complete spheres. It's like a mathematical puzzle where the pieces fit together in a surprising way. You might be wondering, why does this seem so impossible? The contradiction arises because volume preservation suggests that one sphere simply cannot become two identical spheres. It defies our intuition about physical reality. However, the resolution lies in the fact that the pieces created in the Banach-Tarski paradox are non-measurable sets, meaning they don't have a well-defined volume. What are the real-world implications of this paradox? Well, it's important to note that it cannot be performed with real physical objects due to their atomic structure. However, it reveals the abstract nature of mathematical concepts versus reality. It shows us that math isn't always about what we can physically do, but about what's logically possible within a set of rules. In conclusion, the Banach-Tarski paradox demonstrates that mathematical truth can transcend our physical intuition. It reveals the profound difference between abstract mathematical reality and the tangible world around us. It's a testament to the power and beauty of mathematics, where the infinite can lead to truly mind-bending results. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.